Let's deal some more with rotational kinematics. The bridge equations that connect linear or translational or tangential to rotational motion are as follows. The basic idea that I always like to keep in mind is this right here. Rah. And what that means is the tangential quantity is equal to r times the angular quantity. So tangential or linear displacement, sometimes we use a d, but often in rotational motion we use an s, is equal to r times the angular displacement. The tangential velocity is equal to r times the angular velocity. Tangential acceleration or linear acceleration is equal to r times the angular acceleration. So the pattern is tangential quantity is equal to r, which is the distance from the rotational axis, that's what r is, multiplied by the angular quantity, tra. That will help you, I think. An object rotates in accord with the position time function as shown there. Determine the angular velocity. This worked for linear motion. It's also going to work for angular motion. And that is, if we have a position time function and we want to know velocity, we can just take the derivative. So the angular velocity is going to be the time derivative of the position time function. So let's do that. That's going to be 6t squared. We got to power down, don't we? Anytime we differentiate a polynomial, you power down like that. And when we put a 2 in here, that's going to be 24, and that's going to be minus 4, and that's going to be minus 7. So 24 minus 11, how about positive 13? Positive 13, and what's the unit for angular velocity? Not meters per second, but radians per second. 13 radians per second. How about the angular acceleration? The angular acceleration is the time derivative of the angular velocity. So let's differentiate that. Power down. 12t minus 2. At 1 second, what's going to be the angular acceleration? Let's put a 1 in here. 12 minus 2, positive 10. What's the unit for angular acceleration? Not meters per second squared, but radians per second squared. Can the angular forms of the 4 kinematics equations be applied in part I? In other words, up here, could we, if we needed to, use the 4 kinematics equations to help us deal with some other aspect of that motion? And the answer is no. And that's because we can see in this equation, whoops, look at that, I made a mistake. This shouldn't be A, should it? It should be alpha. Silly Mr. B right there, that's alpha, that's not A. Alpha is changing with time, and you can't use those equations if the acceleration is changing. And you can look here, it's changing. Depending on what the time is, the acceleration is going to be some different value. So there you go there. Let's do one more thing here. We dealt with centripetal acceleration a lot when we were studying Newton's laws and force, and that kind of thing. To review, write the simple equation we've always used for centripetal acceleration. I don't know if you remember this, if you've watched any of the other videos, but it's v squared over r. I hope you do remember that, actually. Substitute a bridge equation into the part K answer and simplify to yield another equation for the centripetal acceleration. So we want centripetal acceleration, but now we want it in terms of angular things. And so not linear velocity, but angular velocity. And what do we remember? The tangential quantity is equal to r times the angular quantity. So I'm thinking that v is r times omega. So our centripetal acceleration is going to be r omega quantity squared over r. And what does that simplify to? R omega squared.